Hi guys, today we're going to learn how to find the area bounded by a polar curve. Okay, so first we need a little bit of a review. To find the area bounded by a polar curve, we need to start with the formula for the area of a sector of a circle that you learned back in geometry or maybe in pre-calculus. An area of a sector of the circle is going to be theta divided by the entire circle by r squared. Why I put the entire circle? Because it depends if you're in radians or in degrees. Please remember that for calculus we're going to be working in radians. Therefore, if theta is measured in radians, we have that the area of the sector is going to be equal to theta divided by 2 pi times pi r squared. First of all, why 2 pi? 2 pi is the entire circle, okay? That's why. Okay. After that, you can simplify, you can cancel the pi's, right? And then, okay, you are going to have that the area of the sector, if you remember the formula that you learned and love back in geometry, it was 1/2 r squared times theta. Well, in geometry, you were not talking about the area in terms of radians, but you were using this with degrees back in the day. Maybe you used this one in pre-calculus. Anyway, so what is this sector that we're talking about? In polars, if you remember from pre-calculus, you are going to have some circular-like figures, okay? So if we take a function, let's say the function is going to be r is equal to f of theta, because remember those functions, the variable that we were using was theta, and this theta is in between a and b. And what you have, okay, just stopping here, okay, what you have is that your area that you are trying to find is going to be this shaded situation that we have over here. First of all, let's say that the angle A is going to be here, okay? So when you trace this one, that's going to be your theta equals angle A, which is here. And your angle B, okay, which is in radians, please remember that both of them are in radians, is going to be here, okay? Theta equals B. So what you have is, if you remember from geometry, you were starting at always at the x-axis. Here we're going to start at A. Why? Because they are telling you that your theta is bounded from A to B. So the way that you are going to be moving this equation, imagine that the tip of my pencil is stuck there at the origin. So you start at A and you are going to cover all that area until B. Now what's going to tell you where, okay, how far the pencil should go? This, okay, which is r. That is the function r that you have, okay? That's why you know when to stop here, okay? So that's why you have that the r is an important part of the area of the sector. Now, since we're in calculus and this should give you vibes of Riemann sums, we're going to partition, okay, these sectors that you have over here. This is a huge sector, okay, into equal subintervals. Then the radius of the ith subinterval, let's call it f of theta sub I, and the central angle. What's the central angle? The central angle is this angle that we have from A to B, okay, in case that you forgot, okay? So of the ith sector is going to be b minus a divided by n, is going to be equal to delta theta, okay? Then what do you have, okay? I know that it's a lot of notation, but let me explain you what's the meaning of this notation so it's easier for you, okay? So then the area of the region can be approximated by the area. You have that it's going to be the summation of each, okay, mini sector that we have here. What this is telling you is pretty much you have that the first interval that you have here, or subsector that you have here, is going to be this guy that we have over here, okay? If you have infinitely many, okay, and you add them, what are you going to have? You are going to have the entire area that we have here. This is also A equals theta, okay? So, and this is going to be the first partition, so until we arrive to B, okay? So to get the exact area, as you can imagine, this is screaming integral, okay? Because you have the summation of a lot of infinitely many areas of the sector. So to get the exact area, we can take the limit as the number of the intervals approaches to infinity. So you have that the area is going to be equal to the limit when n approaches to infinity of the summation from I equals 1 to n 1/2 f of theta sub I square delta theta. And you're going to tell me, what in the world is this? Well, this is the area of the sector, just with fancy notation, okay? So it's from here to here, from here to here, from here to here, and you're adding them together. That, as you can imagine, if we do infinitely many sub-intervals, we're never going to end. So the fundamental theorem of calculus, as usual, is here to save the day, okay? This will allow you to evaluate the area by using a definite, happy face integral. So that the area bounded by the polar curve r equals f of theta, whatever is this expression, between, let's call it angle alpha and beta, is given by the formula area is going to be equal to 1/2 integral from alpha to beta r squared d theta. Okay, so this formula that we have over here is going to help you to find, if this is alpha and this is beta, this is going to help you to find the area of a situation like this. Please note that this formula only works for polar equations. So what's going to be the r? The same r that it's going to be given in the hypothesis of the problem. The only thing that you need to be careful is you need to square it. Okay? So let's do some examples so you can see that it's pretty straightforward. Okay, now let's apply the formula. They are asking you to sketch the graph of r equals to 2 plus 2 sine theta and find the area bounded by the graph. So the first thing that we need to recognize here is that you have a cardioid. This, you know this from pre-calculus. Even though we don't need to know the name, I'm going to just write it so you can recall that name. Okay, cardioid. And this, we can see that it's symmetric with respect to the y-axis. Okay, so we have that it's symmetric with y-axis. Okay, so because it's a sine function. Okay, now the next thing that we need here is we need to graph it. Okay, so here you have that 0 is here, then you know that here is pi over 2, then over here you have pi, over here you have 3 pi, and then you are back to 2 pi. Okay, so please remember this is going to be the pole or the origin. Okay, so what are we going to do next? What you're going to do next is I'm going to do a graph. Since this is the first one that we are doing, I want you to understand how to graph it. Okay, so this is what you have. Please remember that graphing is an objective from pre-calculus. So the first thing that I'm going to do, as usual, because the 0 is my friend, I'm going to plug the 0. If you plug the 0 here, what do you have? You are going to be at the angle 0. So please remember that we are having the vector from here to here, okay, all of the way. So we're going to plug the 0 here, so you have that this is 2, so this is going to be the point that we have, okay, with the 0 and 2. Then after that, what you have is you are going to select pi over 2. I would select pi, 3 pi over 2 and 2 pi. Why? To do all the motion of the unit circle here, okay, because I know that it's a cardioid. Okay, now 2 pi, when you plug 2 pi over here, you have that that's going to be 1, so 2 plus 2, that's 4. Okay, so at 2 pi you are here, position yourself here, 1 2 3 4. Okay, so that's going to be your point. Okay, after that, at pi you plug the pi here. Okay, you're going to tell me this is also 2, correct? But remember that now we are looking from here to here, so your 2 is going to be this one, okay, because you are in the polar plane. Okay, then 3 pi over 2, you plug it here. What do you have? You have that that one is going to be -1. -1 times 2 is -2 plus 2, that's a 0. Okay, so technically speaking, here you are back here, okay, at the origin. Okay, after that, what you have is 2 pi. 2 pi, you're going to be back here. So you're going to tell me how you're going to graph it. Well, you need to kind of like remember a little bit of pre-calc, okay? So you start here, okay? Then you are going over here. Then you are going over here, okay? Then you have here, and then you are back to here, okay? So this is your cardioid, okay? That's how we draw cardioid. Hopefully that gives you a good review of pre-calc, and we know that we're back to 2 here, okay? Now, you're going to tell me, okay, so I have this and they are asking for the entire area that we have here. How in the world we're going to find it? Well, here's the rule. For every cardioid and limacon, okay, without a loop, please note without a loop, you're going to use 0 and 2 pi as your limits of integration, okay? So it's going to be limacon without loop, okay, and cardioid. The limits of integration, 0 to 2 pi. Okay, so what are you going to do here? You are going to have that it's going to be the area 1/2 integral from 0 to 2 pi. Why? Because you have a cardioid. Okay, after that, what's your r? R is going to be 2 plus 2 sine theta, okay, all of the square d theta. Okay, so that's going to be your area. Now you're going to tell me, so what are we going to do next? What we're going to do next is you're going to expand it because they are asking you to find it. Okay, so we expand this equation. Let me write it here, 1/2, and then you have that that's going to be the integral from 0 to 2 pi, and you have, when you expand it, you have that it's going to be 4 plus 8 sine of theta plus 4 sine square theta d theta. Okay, you are going to tell me, okay, so this one is nice to integrate because this is a constant. This one has the constant and you can use the formula for sine of theta, but this one not user friendly. So what are you going to do? You're going to use the half angle formula. Okay, what is the half angle formula? What you have is that pretty much sine square of theta is going to be equal, okay, to 1/2, okay, and then you have that it's going to be 1 minus cosine of 2 theta. Okay, why? Because this is way easier to integrate. Okay, if I plug instead of this equation, what do you have? Okay, so let's simplify. 1/2 integral 0 to pi, and then you have 4 plus 8 sine theta. Okay, you are going to have your beautiful 4 there if you want, and then you have, instead of the sine square, you are going to plug 1/2 1 minus cosine of 2 theta, close it, and then I'm going to close my other parenthesis here, d theta. Okay, so that's what you have. Now ask yourself, is this way easier to integrate? Yes. Okay, first of all, this constant that it's a 1/2 and then it becomes a 2. Okay, you can add it to the 4, so let me reduce it so you can see that it's way easier to integrate. Okay, so 0 to pi, and then 4 plus 2 is going to be 6. Okay, that 8 sine theta stays the same. Okay, after that you have that that's going to be negative. Please note that it's negative. You're going to distribute the 4, so don't forget about distributing the 4. You're also distributing the 2, so that's going to be a negative 2. Okay, so you have negative 2 cosine of 2 theta, close it, d theta. Okay, and this is way easier to integrate. Isn't that nice? Okay, so here what are we going to do? You integrate. Okay, so what do you have here? You have 1/2. Integrate your situation. Okay, so this is going to be 6 theta, then this is going to be negative 8 cosine theta, formula. This is going to be also with the formula. Please remember that here you're going to do a u substitution. U is 2 theta, which you have the 2, so it's great. Okay, so it integrates beautifully as a negative sine of 2 theta. Okay, and we're going to evaluate all of this from 0 to 2 pi. Okay, so you have that situation, which is great. Okay, because you know your unit circle, you know that this is going to be what? This is going to be 12 pi. Okay, and this is going to be 0, 0. Super nice. Okay, so you have that they cancel. Okay, because they cancel with the 2 pi and the zeros. It's just beautiful. So you have 1/2. Okay, 12 pi, and then you have that this is 6 pi. Isn't this beautiful? So look at that. Okay, so this is doing it by hand, the first example. I hope that you find this one as easy as I did. Okay, I know that sometimes graphing it is the problem, so just make sure that you remember that from pre-calculus. Let's move on to the next example. So in this example, you also need to sketch and set up the integral expression to find the area of 1 petal of r equals 2 sine of 3 theta. Do not evaluate. Okay, so please note that here you only need to set up the expression. Okay, remember that we are in the polar plane 0. This is going to be 2 pi, this is going to be pi, 3 pi over 2, and we're back to 2 pi. Okay, so here, when you read it, you're like r is equal to 2 sine of 3 theta. So this is not a cardioid or a lemma without loop. This is going to be a rose, okay? If you remember, I'm going to put rose, and the symmetry here is symmetric with respect to the y-axis again because it's a sine, okay? So you're like, okay, we have a starting point there. It's pretty nice. So what are you going to do when you have roses? When you have roses, the first thing that I would do, it would be to let my r, in this case 2 sine of 3 theta, equal to 0, okay? This will help you to find where is the first petal, okay? Because since it's a rose, it's important that you find the petals, okay? So you set this equal to 0, then you clean up that 2, so you have sine of 3 theta is equal to 0. When that happens, you know your unit circle. You know that in this case, 3 theta, it would be equal to many numbers, okay? The first one that it comes to mind, obviously, is 0, then pi and more, okay? They are not telling you that it's restricted, therefore you have a lot, okay? You know that it's also going to be at negative pi, FYI. But this is not your theta. Your theta is going to be, you need to divide everything by 3. Why by 3? Because that's going to be the coefficient of the argument here, okay, of the theta. Okay, so you have that it's going to be dot, 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 and it's negative pi over 3, 0, because 0 divided by 3 is 0, and pi over 3 here. Okay, so these are the values that you have. What this is telling you, and what I recommend you to do, is use the 2 consecutive values of theta as the limits of integration. So since I love my quadrant 1, okay, and you know that this is quadrant 1, I'm going to select this 2. Could you select the other 2? Yes, okay, you can do quadrant 4 if that's your, or whatever, right? Anyway, so we have that. With this being said, it's easier for me even to graph my rows. Let me show you, okay? So, I don't have a lot of space, so I'm going to make my handwriting very small here and do the thetas. Okay, so we have theta and we have r. As usual, okay, I would do 0 first, okay, and I'm using this one, so 0. When you plug 0 there, you have that you have 0, so you start here, okay, and please remember this is your 0. Okay, after that I would do something in between, okay. In this case my friend is pi over 6 because that's part of the unit circle, okay. So I would do pi over 6. What happens when you have when you plug pi over 6 here? You have that that's going to be 2, okay, because this is going to be 1, so 2, okay. After that you would plug your friend pi over 3. Okay, when you plug pi over 3 here, you have that it would be 2 sine of pi, which that is going to be 0. Okay, so you're back there. Okay, so how does it work? Okay, so what you have here, okay, you have that, what was it, pi over 6 is somewhere here. Okay, so that pi over 6, you know that the distance between the origin and the stopping point of your r is going to be 2. So I'm going to kind of like guesstimate your petal is going to be very short. Okay, as you can see, so if this is 2, okay, so something like this. Okay, so this is going to be your first petal. Okay, so this is going to be your first petal. You know that you have 3 petals. Why? Because of the 3, okay, the coefficient of the theta. So your second petal, actually, it would be over here, okay, and your third petal, and this is not proportional, sorry about that, it would be over here, okay, somewhere over here. Okay, so this one I think I did it too long, so let me redo that one. Okay, so it would be something like here. Okay, so you have it. Okay, so anyway, so the first one that you are going to graph is this one. Okay, if you graph this one, okay, that we did, okay, if we want to find the area of this one, what are we going to do? Okay, so you're going to use again the formula. So it's going to be area 1/2 integral. This is going to be equal to what? 0 to pi over 3. Okay, and this is going to be, your r is going to be 2 sine of 3 theta. Please note that I'm not doing anything but using the one from the hypothesis of the problem, square, and then you have the theta. And since we don't need to do anything else, this would be it. Now you can tell me, oh, I wanted to do negative pi over 3 and 0. Yes, you can do that. There's nothing stopping you to do that one. That's fine. okay, and then set up and find the area of one petal. So this is the area of one petal. We're finding the area of the petal in the first quadrant, but nothing stops you to find the area of this one or this one, okay? So you have choices here, okay? Now let's look at another one over here, okay, another type of rows, okay? What's the difference between this rows and the previous one? First of all, we can see that it's a cosine, so this is going to be symmetric with respect to the x-axis, okay, because it's a cosine. But again, you have that this is a rows, okay? Now, since your coefficient of the theta is even, you are going to have, instead of 2, you are going to have 4 petals, okay? So that's the first thing that you see. Okay, after that, you are going to, after thinking about that, you are going to let your 4 cosine of 2 theta be equal to 0 to find the limits of integration. Okay, so you pass the 4 dividing, so you have cosine of 2 theta is equal to 0. After that, ask yourself when cosine is equal to 0. Let's think about the unit circle. You know that that happens at several points, okay? But mainly it's going to happen at pi over 2 and 3 pi over 2. Okay, after that, you know that you have a lot of repeats. So for example, you have negative pi over 2, okay, and there's more, okay? You don't need to use the weird notation that you were using back in pre-calculus, because here we need specific angles, okay? So after that, you're going to divide everything by 2. Why by 2? Because that's the number that we have over here. So you have theta is going to be equal to ... You have negative pi divided by 4, pi divided by 4, then 3 pi divided by 4, and so forth, okay? Again, same situation as before. What I recommend you to do is select 2 consecutive angles, okay? So over here I would select these 2. You're going to tell me why you're selecting those 2, because I know because of the x-axis symmetry this is going to be nice. Give me 1 second and I'll show you how to graph the situation very quickly, okay? So if you have, okay, let's say that we don't know where it starts and all that shows. So what are you going to do here? You do pi over 4, okay, negative pi over 4. If you plug negative pi over 4 here, you're going to have that that's going to be 0, okay? And then you have that at 0, you have that that's going to be 4, okay? Then you have that at pi over 4 is going to be 0. So what you have here is something very, very interesting, okay? The first petal that you're going to have here, okay, and remember this is 0, this is pi over 2, this is pi, and this is 3 pi, okay, and we're back to pi over 2 here, okay? So the first one that we have, which is 0, 4, okay, technically speaking, this one, 1, 2, 3, 4, so we are here. The second one, if you take this one as your second one, okay, you are going to do something like from here to here. Do you agree with that? After that, technically speaking, you would be drawing the petal that it's below. 1, 2, 3, 4. Okay, so you would go here and so forth. Okay, so after that, you would draw 1, 2, 3, 4, this part. Then you go back here. Okay, so 1, 2, 3, 4. It's like this, and then you are back there. Okay, so as you can see, I'm not really good following the original symmetry of the petals, but use your imagination for that. So you can see that we end up here, right? So what I want to do here is I want to find the area of this petal, and this petal is in between quadrant 4 and quadrant 1. Do you see it? So it makes sense that it's this one. Okay, why? Because the negative pi over 4 is over here. Okay, so you know that that angle is over here. Okay, anyway, so hopefully the visual was helpful here. Okay, so I'm finding the petal of this guy. So now, okay, you can find the area. Okay, 1/2 integral from pi, negative pi over 4 to pi over 4, and then you have that this is going to be, the r is 4 cosine of 2 theta square d theta, and that's pretty much it. Now, you might tell me why you didn't use symmetry. I just wanted to use quadrant 1 because I'm just obsessed with quadrant 1. Could you just use quadrant 1? Yes. If you use symmetry, okay, because you know that this one is symmetric, you can tell me that the area is equal to 1/2, okay, and then times 2, and I'm going to show you what. From 0 to pi over 4, 4 cosine of 2 theta square d theta. Why I'm using this multiplying it times 2? Because, well, I know that my drawing is not very good, but you know that the upper area of the petal is symmetric with the lower area of the petal, so that's what you are using here, and that's why you have the 2 here. But this is using symmetry. Please note that I'm so is this more correct than this one? No, both of them are going to give you the same value. Okay, if you have questions about that, you can plug it in the calculator or do it by hand. Okay, so if you have any questions, please let me know. You can write them in the comments, and I hope that you find this video helpful. Bye.